Hi everyone, welcome to the final session of the EDAM Consortium training series. For those of you who have been with us from the start of the series, welcome back. And for those of you who are just joining for today, welcome. We really hope you've enjoyed the series over the past few days. And before we start, we'll just go over a few of the housekeeping rules for the session. Microphones and cameras are disabled for the session, but the chat feature is enabled. We'll be monitoring the chat, so if you have anything you'd like to raise that isn't a question, please post it there. Please don't use the chat to introduce yourself so that we can easily spot anything raised by an attendee. If you have a question, please post it in the Q&A panel. And if someone's asked a question that you'd like answered, please upvote it in the Q&A panel rather than asking it again. We'll address all the questions in the Q&A panel at the end of the session. There's an option to navigate slide to self in case you want to look at a previous slide. This might only appear on some computers. If you see this option, please select the Sync to Presenter option to keep up with what I'm showing. To receive a certificate, you'll need to stay for the full session and complete a feedback form at the end, which includes a short quiz on the content covered. Please note that the session will be recorded, and very importantly, we've seen this asked in a few sessions so far. A recording of the session along with the slides will be shared with the certificate. So we will share the slides and we will share the recording. Just give us a bit of time. You'll likely expect to see this in the next week. Okay, so with that, let's start with our final session. The session for today is how to identify and solve issues with your data. And it's going to be a recipe for analysis-ready data, which we'll dig into in a second. So on our agenda for today is that we're going to start with a bit of background, then move into considering what data you need, how to check your data quality, how to join different data sets together, what you can do with this data set, and finally, how to sense check the results that come from this data set. At the end, we'll tie everything together. So if we're being honest, chatting about data is a bit dry and probably the least exciting of the topics we've talked about in the series. However, it's probably the most important. Over my past visits to Ethiopia, one of the many important things I've learned is that Ethiopians love injera. So to try and make today a bit more exciting, we've come up with a recipe, or together we're going to come up with a recipe for analysis-ready data by following the process of making injera. So if you've ever eaten injera, you'll know it's deceptively simple looking, a fermented flatbread. But getting it right depends on care at every single stage, not just the end. And the same is true of data. Here's the recipe we're going to follow today. 5 steps to get from raw data to something that you can actually trust and share. We start with ingredients. In other words, what data do you need? Then we check these ingredients, which means checking if your data is high quality. Once you're happy with ingredients, it's on to mixing and fermentation. So joining your different data sets together and assessing any issues that arise. Next, we need to test the batter and cook it. In data terms, this is exploring and then modeling if needed. And then finally, tasting. Do the results of this whole process make sense? And now, I do acknowledge that the final 2 steps do extend slightly beyond getting analysis-ready data and actually looking at the data, but I think it fits into what we want to present today. So just a bit of background of where the session came from. The examples in the session come from real work we've done in tandem with our partners in Ethiopia, looking at growth monitoring and promotion services and perinatal health. Our goal today is to share what we've learned from those use cases, as well as share some of our broader experience working with the data. But I want to flag something important up front. This is a recipe and not the recipe. Every data set, every question, every context is a little different. Just like cooks adjust the injera batter depending on the theft, the water, the weather, there's no one-size-fits-all solution here. So treat everything that you hear today as a set of habits and checks and not a rigid formula. So let's start where any cooks start, with the ingredients. What data do you actually need? So before you touch any data, you need a question. Data doesn't exist in a vacuum. It exists to answer something. So much like deciding what ingredients you need before you start cooking, ask yourself, what data do I need in an ideal world? Then ask, what's actually available in Ethiopia? If it's not available, is there a similar setting or a proxy you could borrow from? And then finally, what could you feasibly collect to do better next time? And as we work through this presentation, always keep this in mind. Your data is there to service a question. So you always keep the question in mind when you think of this entire process. You're essentially asking, in terms of ingredients, what ingredients do I need for this dish? And if I can't, what ingredients do I need for this dish? And if I can't get the exact one, what is my substitute? So when you think about the data you need, one data set is rarely enough. You'll need to think about your data, your outcome variable, and your explanatory variables separately. Diseases and health outcomes are multifactorial. So often you're pulling from things like population data, individual level data, genomic data, environmental data, economic data, and more. Don't expect a single data set to carry the whole analysis. However, keep in mind that having multiple data sources adds complexity. So you really need to strike a balance here. And we'll see later in the session, we need interoperability between different data sets for them to actually work together. Now think about packaging, and this is how your ingredients arrive. So how your ingredients arrive matter almost as much as what they are. Imagine receiving a huge sack of Tef loose versus in manageable labeled bags. This is how you can think about the difference between a well-chosen data file format and a poorly chosen one. For tabular data, CSVs are normally fine for small data sets, but they don't scale well. For millions of rows, look at things like a RDS file or a FST file in R or Parquet files if you want something that works across other languages. And a practical warning here, I know we all love Excel, but Excel isn't stable for very large data sets, so please keep this in mind. For spatial data, and we'll dig a bit more into what spatial data is later in the session, use shapefiles for vector data. So these are things like points, lines, polygons, raster files for gridded data, and netcdf formats for things like climate and remote sensing. Now, you may recognize the slide from one of the slides Gina presented in session 1. I've repeated it because it's important, and it's important to emphasize that the format for the task is important, especially given that the datasets we'll work with now are much, much bigger than previously. Don't let the storage format become your bottleneck before you even started analyzing your data. Okay, so now that we've got our ingredients, before we can mix anything together, we need to check them individually. This is quality control before we combine anything. And so an aside before we actually dig into some actual data quality dimensions. Good data quality starts with capturing and recording it properly. No amount of clever analysis downstream can fully replace data that was captured incorrectly in the first place. It's a bit like using spoiled and mismeasured ingredients. No technique in the kitchen fixes that. So these are some things to keep in mind. Any project where data is captured should keep a clear record of assumptions and collection details for every data set. It should maintain an up-to-date codebook, and it should invest in training field workers and data capturers. You should always consider them as being part of the entire process. In addition, when recording data, there should also be built-in validation texts that catch incorrect entries as they happen. So related to this point, here's a bit of food for thought. And we'll have these sort of food for thoughts interspersed throughout. And it's just things you should think about or just keep in the back of your mind. I don't have the answers to them. So it's sort of an open call, maybe for people in this call, to think about whether there's a way we could come up with a solution for the problems that are raised. And so the food for thought on this slide is thinking about AI. And if you attended the session yesterday, you would have heard about, you would have had an introduction to agentic AI. A question I have is whether we can use it to help catch incorrect data entry before it ever reaches the analysis stage. And then to add on to this, thinking, do we even need AI to do this? Okay, so on to actual data quality dimensions. So imagine you do have data that's being collected, you have no control over that, and now you need to assess what the quality is. There's many different frameworks for data quality. The one I've chosen here today is based on 6 dimensions from the UK's Government Data Quality Hub. So we'll step through each of the 6 in turn. The first is accuracy. And this means, does the data reflect what is really happening? Or sorry, does the data reflect what has really happened? The next is completeness. And this is there anything that you need that's missing? And that's very important. When we look at completeness, always look specifically at the data you need. Third is uniqueness. So are there any duplicates? And we'll see in a future slide that this also extends to sort of how we consider scale. So you can have duplication across different scales, either spatially or temporally. Fourth is consistency. So do your values agree with one another? Fifth is timeliness. Is the data available in time? Is it available in time to be used? And sixth is validity. So does your data match the expected format? Think of these as your ingredient checklist. So think about sort of, is the flour actually teff? Is there enough of it? Is it ground correctly? Does it agree with what's on the label? Is it fresh enough to use? And is it right for this recipe? You kind of extend this analogy to data, and you have these dimensions that you want to try and score your data on, or at least use as a guide to assess data. For anyone who's worked with data, we know trying to assess data quality is really difficult. So you can sort of use this as a framework. So now that you have this framework, how can you actually check for these or assess these in practice? I'll give a few suggestions, but of course, there are many different ways that you can actually do this. For accuracy, check whether the data are within plausible bounds. So this is considering something like, are percentages between 0 and 100? Is height in meters as opposed to centimeters? These sort of things. Next is completeness. So check for missingness. And very importantly, if you can, understand why it's missing. And we're going to dive into this in the next slide in a bit more detail. For uniqueness, check for duplicates. And this is both within a data set and after you've joined data sets together. For consistency, here you want to consider whether related fields agree. And again, this is both within a data set and across data sets. So this is thinking about things like, if two data sets have a person and a date of birth recorded, do those agree? And within the same data set, if we capture a person and the date of birth twice, do those agree? Fifth, timeliness. Thinking about this is there's sort of two ways. One, you need to consider, has time affected accuracy? So is my data relevant enough? And then a second one, which probably affects public health problems and especially infectious disease problems more, is how long is the lag between when the event actually happened and when it's captured? Reporting delays are a common issue for epidemiological models that we need to consider. And then fifth is validity. Does the data conform to expected types, formats, ranges, and categories? And this final one especially matters for location names, which again we'll come back to later in this presentation. So again, another food for thought and sort of an open challenge is, can we create a consolidated data scoring system for Ethiopia and more broadly based on checks like these? So is there a way that we can come up with scores or come up with a framework that every time a data set is made or every time updates are made to a data set, we can have a score and say, yes, it does well on this, or no, it does badly on this? Because it's really important, because a handful of cheap automatable checks like these could catch the majority of data entries before we ever get to the analysis stage. And so a final thing to highlight on this slide is throughout the rest of the session, some slides will relate specifically to these dimensions, which have been flagged in the title. So keep an eye out for this. Okay, so I said we would come into or look at completeness a bit more. And with completeness, there's two things we want to know. We want to know, is the data missing? But then we also want to know why. So consider this missingness map on the right. It shows you where the gaps in your data are, but the patterns of these gaps matter more than the raw percentages themselves. So in some cases, the gaps might be scattered completely at random, which is shown by sort of the arrow, the block 1 there. In other cases, a particular district or time period may be missing and something more systematic may be going on. And then in some cases, an entire column with the vast majority of its variable is missing. And in these cases, there's really nothing you can do, and you might need to drop the variable completely. So a map like this tells you where the gaps are, but you still need to work out the why. So how do you actually figure out the why? And to make this, I often get confused about different types of missingness. So to make this a bit more tangible, let's ground this in a scenario. Let's consider children who are being weighed at health posts every month for the GMP register, but not every weight makes it into the data set. And so one common framework groups missingness into 3 categories. Again, there's different ways we can consider missingness, but this is just one of the ways. So the first type of missingness that we consider would be missing completely at random. So this is where missingness is unrelated to the data. And so using our scenario here, this would be where, for example, a scale's batteries died. It has nothing to do with the child, the post, or the weight, but if the scale is dead, the data is not going to make it into the data set. Next is missing at random. And this is missingness that depends on something observed in your data. For example, imagine the scale at a specific health post is missing or faulty, and here we know then that missingness depends on the specific post. So the issue is tied to this post. And then finally, we have missing not at random. And this is sort of the worst case. So this is missingness which depends on unobserved data. So for example, in our scenario, consider a case where the sickest children never come to be weighed. Missingness depends on the thing you're trying to measure, but because they don't come to be weighed, you never capture it. So it's difficult to understand the reason for the missingness. And this type of missingness is the one you have to be particularly careful about. Because in our scenario, if, for example, these are the children that are missing, when you try and get insights from the data, you're leaving out the sort of cases that you'd want to see the most. Okay, so if you know why the data is missing, what can you actually do? So for missing completely at random, usually dropping the missing rows is safe. You lose statistical power, but not validity. And of course, if the data set's large enough, which often with the sort of problems we considered is, we don't even need to worry about statistical power. Imputation is also an option, but often not necessary. And just as a quick explainer, imputation is where you fill in missingness in your data set based on other values in there that you assume are sort of similar or can tell you about the missingness. However, it's worth flagging that missing completely at random is a strong assumption, so don't assume it by default. For missing at random, dropping rows can bias your results because the thing you're dropping is sort of systematic. So in these cases, imputation may help, but the imputation would need to be based on the source of the missingness. So you need to complete rows using something related to the thing that's missing, if that makes sense. So in our example, the imputation would be based on health posts. And then finally, missing not at random, which I mentioned is sort of the most nasty case, dropping can bias you, but the problem is you don't know what to impute over because the values itself that you would need to kind of learn from are missing. So here you need to go and investigate the cause directly and also test or test how sensitive your analysis is to the missingness. And the way you can kind of think about this is if you know the source of the missingness, then missing not at random becomes missing at random. So a quick aside on imputation. Imputation is a bit like absinthe, the fermenting agent in the injera batter. Too much of it and the injera becomes powdery with no eyes. Too little of it and the injera becomes powdery with no eyes, and too much of it, it turns soft and falls apart on the pan. Similarly, filling gaps can just as easily wreck your data set as it can rescue it. So be very careful with imputation and if you're going to use it. So what should you do? First, ask why the data is missing. If it's missing at random, use multiple imputation, which captures uncertainty rather than just plugging in a single value like the mean. Consider whether a complete case approach might also be preferable. So in this case, that just means dropping missing rows. And then also try a few different options and see if your conclusion changes. It's always good to test the sensitivity of our assumptions or the sensitivity of our results to assumptions we make during data cleaning. And no matter what you do, always report it. Throughout the session, something I'll repeat over and over and over. With data cleaning, be very specific about what you do because how you clean your data impacts the results you present. And so a final comment on data quality is related to uniqueness. So I mentioned when I presented the slide that when we think about I mentioned when I presented the slide on data dimensions that we think about uniqueness normally about duplication. So is a row repeated? But duplication isn't just about repeated rows. It also creeps in through aggregation and across spatial and temporal scales. You cannot disaggregate data down to finer resolution than it was collected without making assumptions. This is another thing to keep in mind. So what should you do? Well, you should record your data at the smallest unit you'll actually need, both over time and spatially, and aggregate upwards from there. And so just to add in here, I'm assuming that mapping from a lower admin level to a higher one is known. So you do need to know the mapping to go from sort of lower to higher. I'm sorry. Okay, so now that we've checked our ingredients individually, it's time to mix them all together. So now I want you to imagine in your head is we've checked every individual data set that's relevant to the question that we want to answer, and now we need to join them all together. And so once we've joined them in together, this is also where new problems may sort of bubble to the surface. So mixing and fermenting is about joining the data, but then also sort of going through a whole nother stage of checking what comes out. So to join data sets, the main thing you need is a shared identifier that links them. This is a common key between the two that tells you how one thing connects to another. And this is the main thing for interoperability. We spoke in previous sessions, we may have spoke about a personal identifier for people or something like this. You really need something that can link things together. For tabular data, this is usually more straightforward, but this becomes much harder once spatial data is involved. And I have a map on the right, which sort of shows the result for spatial join that I'll get into in a few slides. But two warnings here. When you join data, one, joins can create missing data when keys don't match between data sets. And this is sort of the problems that I was talking about bubbling to the surface after a join. And when this happens, your instinct should be to find and fix the mismatch, not to fill in gaps as if it were ordinary missingness. And it's very important to sort of hammer this point home, that the missingness we spoke about previously is different to missingness that arises from joins. And then the second warning is that you're limited by your course's data set. So expanding a bit on what I mean by you're limited by your course's data set. Here's a worked example. Let's consider the scenario. Let's consider the scenario where we're asking the question, does drought drive childhood stunting in Ethiopia? Now, a sort of loose causal chain here would be that poor rains lead to crop and livestock losses, which then lead to household food insecurity, which then lead to impaired child growth. And this is kind of what we're thinking and what we want to try and look at to answer this question. Next, look at the square at the bottom. These are the data sets that we have and the data sets that we want to use to answer this question. Stunting records start at the Kabele level. They're monthly and it's from 2015 to 2025. Rainfall is a 5-kilometer gridded climate data. We have it daily and it goes quite far back from 1981 to 2023. This is really our most granular and powerful data set we have. Population projections are at the Warida level. It's annual and it's from 2007 to 2024. Now, once you have these, the issue is you can only analyze at the coarsest common denominator across all of them. So even though rainfall is very granular, you need to look at what's common across everything. And in this scenario, the coarsest common denominators across all three would be Warida level, it would be annual, and we'd only be able to look at data where all three overlap. So that would be 2015 to 2023. So again, this is very important to keep in mind, and this is one of the things I mentioned when we considered that interoperability and including more data sets can change what you can look at the end. And now returning to a different issue that I mentioned. Even after you've got the data, and even after you've got the data to the same scale and coarseness, you still need to join this. And in this example, it means joining spatial data. So spatial data bring their own complications. Each row in a shapefile defines a polygon, and you can join a point to a polygon in a few ways. And so just sort of rewinding a tiny bit, our goal with spatial data is we'll have a shapefile so that if you look at the figure on the right, that's the OCHA shapefile. We'd have a shapefile without any values to attach it. Then separately, you've gone and generated a data source, so you have a tabular data source where you have values attached to a Warida, and you want to say, how can I link those values to the shapefile so I can view it visually? And that's kind of, again, what you can see on the right. On the right, it's looking at children who have been weighed by GMP services, joined to the OCHA Warida for specific years. So you have these sort of data points and you have the shapefile. You can join them in a few ways. One is by name. Another is by coordinates. So let's say you have a latitude and longitude of where a value is. You want to see where in this big polygon does that point fall, or by overlapping different polygons. Now, there's usually two elements that make spatial joins fail. The first is joining on inconsistently defined location names, and the second is using inconsistent coordinate reference systems across data sets. And we'll get into that's also known as a CRS, and we'll get into that in the next few slides. So starting on joining spatial data by names. So again, I'm just going to jump back to the previous slide. Keep in mind that what we're doing here is we have children who have been weighed by GMP services. We know the woreda they belong to, and we want to now try and join this to a shapefile. So we have a file that says, this is what a woreda in Ethiopia looks like. We know the name, and we're trying to join these two things together. Trying to do this by name is one of the most common and often silent ways a join goes wrong. And the reason for this is the same place can be spelled differently across data sets. And there's a few examples of where we've actually seen this across the work we've done in the square on the right. So as an example, one spelling may be Addis Ababa versus Addis Abeba, or we might have SNNPR and versus SNNP, and then region spelled out. Every mismatch like this is a row that quietly drops out of your join. The main point to hammer home here, which I think I've also sort of touched on in the previous slide, is location names should never be your spatial identifier. A single typo loses the entire row, and a non-standardized naming system blocks you from mapping to any external data. So what should you do? Well, you should use a stable location ID or longitude or latitude as your unique spatial identifier. So have something that's unique, that doesn't depend on the actual name. But to do this, it means you need to adopt sort of a standard and have this across all the data sets you use. And then if you're going to use a location ID or a longitude or latitude, you should also keep a master list mapping these coordinates or ID to place names with a changelog over time. So have some master list where we can see, okay, here's an ID, here's the name it belongs to. And then always use that ID so that the name is only defined once. I've shared two links that you can look at your own time on the bottom right. The first is an open source tool for faster geospatial dataset prep, and the second is a particular tool from the suite, which helps with reconciling inconsistent names across different datasets. Okay, and so on to the second issue, which is a coordinate reference system, which I mentioned is also called a CRS. Or called CRS, abbreviated CRS for short. A CRS is how you turn the Earth's curved surface into flat coordinates. There are two families here, a geographic coordinate system, which is degrees on a geoid, and you should be more familiar with this. It's just longitude and latitude. And the second is a projected coordinate system, which flattens things onto a map in meters or feet, and it's more comparable where these squares that we sort of use are roughly equal size, or may have ways that makes comparing things like area distance easier. The main issue to be aware of here is if you mix the two without realizing it, the same location ends up with two very different sets of coordinates. And a classic symptom of this is you may have points that should be on land that end up in the middle of the ocean. So what should you do? Well, one is match the CRS across every layer before you join anything. Use a geographic system by default, unless you're measuring area or distance. Then if you're doing this, switch to projected system. And then finally, always plot your points on a map before you analyze. If something looks very out of place, consider checking your CRS because it might be wrong. Now that all our ingredients are mixed, before we commit it to the meathead, we need to test the batter. So in other words, this is exploring your data first and then determining what you need to do to answer the question. So before you analyze anything, make sure your outcomes actually comparable across groups. And in public health, this usually means adjusting for group sizes. This is one of the biggest sort of errors people make before they analyze data is you clean everything, but then you don't get an outcome variable that's actually telling you something meaningful. And before I explain this a bit more, let's look at an example. Consider testing for a disease. We have two separate groups and we don't know how big the groups are. Someone says that there's one case in group 1 and one case in group 2. If you just have this information, you may assume that severity across both groups are the same. But then if we take a deeper dive and someone tells you there's 20 people in group 1 and only 5 people in group 2, we now know that this tells a very different story. In cases of group 1, there's only the proportion of people infected is only 5% or 0.05. Whereas in group 2, it's 0.2, so 20% of the people infected. And so this is a very, very different proportion of people infected, and it's telling you something very, very different. So it's always important to scale and use your group as context. So there's two ways you can do this. Best case scenario, you have a reliable denominator. So this is something like population. And when you have this, scale by this. So for example, turn a count into proportion or rate. The trickier part is when you don't have a reliable denominator. You still need to find a way to compare these counts directly, but it's a bit more difficult. So some examples of what you could do here is you could look at a ratio. So maybe look at a ratio between males and females between both groups. You're still impacted by population size, but it's slightly more meaningful. You could also look at rates of changes over time, or you could also look at something like the coefficient of variation. Again, this is caveated because there will still be some impact by the group size, but it's much better than just looking at counts alone. So the core point here, and what you really need to do, is that if two numbers come from two different size groups, you must scale them before comparing. Otherwise, what happens is group sizes could masquerade as signal. And so a bit of an aside on this, because sure, having population data, it's easy to scale if you have the population data, but we know that this is a lot more difficult in practice. So two of the quality dimensions I mentioned earlier was accuracy and timeliness, and demographic data is one of the sources impacted by this the most. And the reason for this is demographic data is hard to collect. So over time, its accuracy and timeliness degrades. Now, we know this is a problem that affects the entire world, but in particular, Ethiopia too. Ethiopia's last full census was in 2007, and between counts, we have to rely on projections which carry their own assumptions. And these assumptions can be thrown off by things like high displacement, which are also difficult to measure. And then as a separate aside, stratification across these matter too and can change over time. Stratification, especially things like sex, does matter, and we do need to account for them and consider how this changes in our predictions. So what should you do? Well, there's really not much you can do apart from rely on these predictions. But what you should do is be explicit about your demographic data sources and the assumptions your data source makes. Also, if possible, and you have the time, run a sensitivity analysis across different demographic sources to see how much your results actually depend on the source you've used. If your results change by changing a source, it means that you have quite high reliance on the actual source you've used, and that's something that you should flag when you present your results. So I've added a few useful demographic sources on the right if you're interested. And so these have different shapefiles that you can use, and also different population projections that are quite helpful that you can use to compare when you're trying to find a denominator for your data. Okay, so now that you've joined your data and you have the outcome variable you want to measure, it's on to the batter test in our analogy. So again, you need to check the consistency of your mix before it ever hits the meathead. In data terms, this is exploratory data analysis, or EDA for short. EDA can reveal problems, but it can also build your understanding of the data. And again, just a point, because we're going to touch on it next. In our analogy, once you're done with the batter test, the next step is cooking, which in our case is answering the question. So you're trying to explore the data, check everything, and then answer the question. And often answering the question will be done with modeling. But as Gina explained in session 1, modeling is often suited to a particular type of question. So in some cases, we're going to do this exploratory analysis just to check what the data looks like. But sometimes this can also answer your question without needing a model at all. This is always important to keep in mind. And I said this in earlier slides, always keep the question in the back of your head. And as you're doing things, remember the point of cleaning data and getting analysis ready data and actually analyzing it is to answer a question. So what are three useful EDA checks that you can do? And again, caveating this as I have with most of the slides, but this is not exhausted. It's just sort of some starting checks that you can do. First, you can look at distributions. So plot every key variable, look at sort of histograms, look at count bar charts, and then also check what outliers there are and against what is plausible. So for your outliers, look at something where there may be an impossible value that's crept in, even though you've done checks. Maybe you'll see age of 155, which you know is a data error. Maybe that should have been 15 and an extra O is crept in. Next, look at plots over time and space. A sudden gap or step could be an artifact or not a real trend. So it's very important to spend a lot of time when you do see something out of place here. However, sometimes these plots may reveal a genuine trend. And these are the cases where we may already be able to answer certain types of questions. And the questions I'm thinking about here is, let's say, for example, we're considering GMP and we want to know, is service provision getting better or worse? Sometimes a line plot or just a simple plot over time or space can answer this without needing any models. And then finally, look at relationships. So cross-tabulate and generate correlation heat maps between variables. And this can reveal potential risk factors and inform how you build your model. But similar to the previous point, it can also flag clear enough risk factors that could be good enough to answer a question, or at least be a starting point to start thinking about interventions that we want to build on based on these risk factors. And again, along the way, as you do these EDA checks, they might also help you think about how you want to refine your question going forward. But what if we do actually have a sort of question in mind? But what happens here if we do actually need to model? So we've done the EDA, we've looked at some explanatory plots, but we've decided, no, we still need a model to answer this question. Well, here's a few things you should keep in mind. First is, before you model, document every data cleaning decision and freeze an analysis-ready data set that you can always point back to. So have your data set versioned and know what you're using to model. While you're modeling, document any data problems that the model uncovers itself. So for example, consider you've done a regression and a wild coefficient appears. This could be a finding, or it could also be that it's a data error. And this is something that you need to try and figure out. And then after you model, if you found any errors, go back and fix these in the raw data set, version your data set again, and then rerun the whole thing from scratch. So again, I sort of say this with a grain of salt, because in practice, whenever I do things, sometimes you tweak and you run models and you tweak as you go along, but it's always important then to go back and make sure you have a version of the raw data set with these changes. And so again, here's some food for thought. When making, and this one's specifically related to Injera. When making Injera, once the batter hits the meathead, you can't add water back in. And in analysis, it's very similar. Once you start to model, your data prep should be locked in. And you should have a versioned data set that you can point back to. Okay, so on to the fun part, the tasting. So now that the Injera has been made, before we can serve it, we taste it. And in data terms, this is asking whether our results actually make sense. And this is regardless of whether you've done EDA or something descriptive, or you've actually built a model to answer it. So does it taste right? How do we do this? Well, you need to sense check your outputs. So again, no matter what analysis you've run, check your output against what's known. And so here's 4 potential checks, not exhaustive, there may be more, but these are 4 good starting points. First, check your results against known benchmarks. Do your rates sit near published national estimates or estimates in the literature? So if you see something like an order of magnitude gap, it usually points to an error in the units or denominator error, or it could just be a data entry error. Check it against theory. Does your effect point in the direction theory expects? And are they plausibly sized? So for example, here, if a protective effect for a known risk factor, if you find a protective effect for a known risk factor, this may be a red flag. Check your results against totals. Do your modeled counts reconcile with the raw totals you trust? And if not, when you find a mismatch, this could signal a join error or double counting. And then finally, again, I said this throughout this presentation, always check sensitivity to your choices. Would a different, equally reasonable choice flip your conclusion? If the answer is yes, your method is driving your results, not the data. And again, across all of these, it's always important to keep in mind, maybe sometimes you do have a different result. So it is possible that maybe you find a protective effect or you find an order of magnitude gap and your results are just different. And that is okay, but always be sure about it. And so on that note, another food for thought is, A result that you can't explain to a domain expert isn't ready to serve. So interrogate it before you entrust it. So you don't need to know it completely, but just be confident of what you're presenting in the domain. And with that, we've sort of reached the end of our recipe. So in the last 5 minutes, what I want to do is conclude with the last step, which is writing it all down so you can make your Jira or make your analysis ready data set again. So it's important to keep track of what you've done, both so your analysis is reproducible and also so that you can reuse the data set for other work later. And here's 4 things to keep in mind that can help you do this. 1 is script it, don't hand edit. So make every change in the code and never do this by hand. This is important so that what you did to the raw data can always be reproduced. The next step, which we said before, is notice throughout. Quality isn't a final step. It's something that you can check and address at every single stage. 3rd, save your Ursula. So in data terms, that's your clean data set, your code, your metadata, and a written record of your decisions. This is the starter for your next analysis. And again, emphasizing here that saving what you've done is more than just saving a clean data set. There's a lot that goes with actually saving a clean data set. And then finally, remember the feedback loop. If your analysis reveals a data gap or a better way to frame the question, go back and address it rather than forcing your analysis to poorly fit the data you already happen to have. So when you do analyses, it's always okay to go back and adjust things. It's never okay to go back and adjust analysis to get the answer you want, but it is fine to go back and reframe things based on what you see from a first pass. So let's end on the recipe we started with. This is the same slide, but what we now have is the steps or descriptions of what we've covered throughout the session. So ingredients. Start from the question and pin down the data, the scale, and period you need. Next, check the ingredients. Inspect the quality of each data set before you try to mix them together. On to mixing and fermentation. Join on shared codes, align your CIS, and then read what the combination reveals. Check missingness based on joins at this stage, not based on different types of missingness, and don't try and impute, rather try and fix where there's been errors with the join. Onto the batter test and cooking. Scale your outcomes and then explore the combined data. Sometimes, and always keep in mind, sometimes a simple answer is enough. Only model if you need to. And then finally, tasting. Sense check every result against what you already know before you serve it. And with that, I'll end the session on this core idea. Making data is like making good in Jira. It's important to follow the correct steps and be careful along the way. You don't fix bad in Jira or bad data at the end. You learn to notice problems throughout the process. Thank you. So we have a bit of time for Q&As before I'll jump to sharing the feedback form, the link for the feedback form and the QR code. Cool. Yeah. I might look at Gina's computer just to see if there are any Q&A questions. And again, just a reminder, we will share the slides and we will share the presentation with your certificate. So you will get all of these. So on to Q&A. I'm not sure if there are any questions in the...
Do you want to just raise this as well? Someone asked for the form for Monday and I shared it. Go for that for today.
Okay, so very importantly, someone's asked for the feedback form for Monday. Gina has shared it. That is not the feedback form for today. So please, very important, when you open the feedback form today, it should say session 3. We haven't shared that form yet. We will share it shortly.
Yeah, and we have some questions.
Okay, so there's some questions. Okay, we're going to start with a hard question, which is, what are the methods to identify the type of missingness in the large data set, because data sets cannot be expected manually, and which imputation methods are most suited for multimodal healthcare data? This is a difficult question. I'm not sure if I know the exact answer to this. I think it's really difficult. So I'll start. I feel like there's 2 questions in there. For the first part, the methods to identify the types of missingness in large data. Really, the only type of missingness you can sort of systematically, or at least computationally look at, as far as I understand, is missing at random. So that was the MAR case. And this is where something systematically is wrong. And so there's no automated way to do this, but what you can do is you can try and summarize where the missingness is. So for example, let's go back to the health post example. Consider we know that there's missingness in our data set, and we group by health posts and see how many data points are missing. If a particular health post has some sort of missingness, or has a higher percentage of missingness, then we may assume that's systematic. If we look at these summaries and we can't see anything, then it may be missing completely at random. Again, the issue with this is that if there is no pattern, it might be missing not at random. And here we need to understand the process and try and look at it. So this is one of the things I think that statisticians argue about, and that there's no one-size-fits-all solution, which is always seems to be the answer to these types of things, is that you kind of have to figure it out as you go along. But tangibly, the starting point would be to try and see, so tabulate the percentage of missingness and see if there's anything systematic that you can see going on, and tabulate this missingness across different variables you have. Which imputation methods are most suitable for multimodal healthcare data? So again, I mentioned I'm not an expert on imputation, but when you do imputation, multiple imputation is best. So this is repeating imputation over different subsets. There's different examples of how you do this. Mice is a common one, at least for tabular data. And the main idea here is that you impute multiple times and you have some sense of uncertainty. So, in this example with mice, and I'm really paraphrasing how it's done, or how multiple imputation would be done, but it's, imagine you try and figure out what's missing based on subsets of the data 500 times, and then you quantify how different those are to capture uncertainty. For multimodality extending beyond tabular data, so let's say text data and image data, I'm not sure, if I'm being honest. So I'll have a think and try and get back to you. But that's a very, very interesting case. And I think that's something that's sort of actively being worked on at the moment. Sorry, okay. No worries. And sorry, I've got to jump to there's some FAQs on the screen that you may be wondering. Okay, on to the next question. What is the most effective methodological approaches for handling missing not at random data in statistical analyses? Again, missing not at random is a really difficult case, because you need to try and go back to the data process and somehow stumble on what's systematically gone wrong, so that you can go from missing not at random to missing at random. If you can't do that, the best you can do is sort of test sensitivity to the missingness. So you can try run the analyses multiple times by sort of changing your assumptions based on the missingness. And there's different ways to do this. To be honest, I'm not very sure about the exact statistical approaches that you can use to do this, but there's ways to essentially test how sensitive are my results to this missingness, which we will, if there's time, I'll have a look at your name and email, and I'll try to get back to you on this. That's a really good question, by the way. Is clustering important in machine learning when integrating data from different data sources? And then what are the opportunities and challenges related to integration of different data sources in Ethiopia? Can we really get a national representative individual level data with other than the DHS in Ethiopia? Okay, so I guess those are two different questions. Also, sorry, I haven't been swinging over to Gina at any point, but if there's anything to add in, Dr. Gina Charney's also here, and Catherine Thorpe. So if there's anything, just, chip in. Going back to the questions, if I can see them again. The first was clustering. I mean, I think clustering is important before you join data sets. Sorry, let me just regard my thoughts. I think clustering is important, but it's clustering in a different sense. Like I said, I think when you're joining data sets, what you want to look at is clusters of missingness, as opposed to whether clusters exist in the data set. So I think from an analysis perspective, you want to look at clusters. That's sort of a separate question. And then on to there's a lot of questions. Sorry, back to the... I sort of lost my train of thought. Sorry, yes. So to answer that, yes, you should cluster, but it's a different type of cluster. Cluster missingness. And then what are the opportunities and challenges related to integration of different data sources in Ethiopia? And can we really get a nationally representative individual level health data? And the opportunities and challenges, I guess, those are some of the food for thoughts I raised throughout the presentation, which I'll share. And the stuff that I think even as consortium we're interested in, it's how do you consolidate these things and prevent data entry issues. And so that's sort of from one perspective is how can we consolidate things going forward? And then the other issue is how can we retrospectively fix things that have already been captured? And those are two sort of separate issues and challenges. And then can we really get a national representative individual level health data? Yes, again, I think it's possible, but the problem here is that prospectively doing this is much easier. So I know there's countries like Denmark, which do this really well. There's national identifiers that get attached to health data, and it's easier to track their data based on this. But this is something prospective that we can plan for. Going back and doing this retrospectively is much harder. Yeah, I hope that answers the question. Okay, since the 6 data quality measures may have different scales and levels of importance, are there any alternatives other than simply averaging them to assess overall data quality? That's also a great question. And again, with the food for thought, I guess that's something open. That's an open for discussion, a point sort of open for discussion. I suppose one scenario thinking out loud here is that you could weight things. So let's say in an epidemiological analysis, perhaps accuracy and timeliness is more important. So having data, like in an ideal world scenario, we might have data reported on the day it happens. That might be more important than if we're looking at something retrospectively over time where we know it's been reported 10 days later, but we can adjust for that because it's not as important to have timely data. So I think the way we combine this depends on sort of use case to use case and problem to problem. And again, I do agree, maybe simply averaging them isn't the best case or isn't the best way to do it if certain dimensions matter more than others. Okay, I think this might be the last question, and then we'll go on to the FAQs. Thank you so much for all the questions. They're very, very interesting, and hopefully I'm answering it well. But if you do want to follow up, I think there might be a section in the feedback form, but also feel free to reach out if you want any further information. Okay, and so the final question is, hello from Ukraine. Are there any ways to address the issue of population figures in countries at war? For example, in Ukraine, the government has restricted access to population data. Millions have left the country and millions have moved to other regions, both with their own regions and to other parts of the country. We don't know where the population is located or how many people are there. How can we resolve this issue so that we have reasonably accurate figures and can model the spread of the epidemic? Again, I think it's a very interesting question. And then tying back to the Ethiopian context, I suppose there's a similar thing with a lot of displacement. And even with climate, we can think of this with these climate events. And again, I might take an easy ouch here, is that I think it's very difficult to properly account for this. I think if you have rates of displacement, then you can look at existing population measures and try to adjust by this. And I'm sure there's probably better answers in the literature related to this. But I think, yeah, again, off the top of my head, it would be trying to look at existing displacement statistics and then see if you can adjust the population based on that. But I think, again, there's probably better answers in the literature, and this is probably something I'll get back to. I'm not sure if Gina wants to chip in on this because I think probably has more expertise than me.
Yeah, it's very difficult to accurately account for these kinds of things. The best way at the moment that people seem to tend to be doing it is there is a number of like satellite-based products that allow you to identify damage and where we actually think that people might be living. It's very difficult then to know those people's location, but you can get a better idea of how many people are actually living there. So we can use things like nighttime light images, which are satellite-based images that are taken all of the time, and it helps us to sort of have a crude estimate of how many people are there versus how many people have left. But knowing where they've gone, like you said, is incredibly challenging. There are ways of modeling it, and I recommend if you're really interested in the topic, there is someone called Andrew Tatum, and he works at the University of Southampton, and he's very big on this and how to account for people that move all the time in ways that we don't fully know where they've gone. So there is a wealth of literature on this as well, that would probably be very helpful for you. So yeah.
Yeah, and I think that's a great answer. Like I said, Gina, definitely more of an expert related to that. Related to Andrew Tatum, on one of the slides is a link to World Pop. So if you click on World Pop once the slides have been shared, I think that's also his sort of product. So have a look at that, and then I think you can follow through to finding him. Okay, I think that's all the time we have for Q&A. So in the last 5 minutes, as before, please complete the feedback form. We've mentioned throughout the sort of seminar series that this is the first time we've tried to host a seminar series. It's very much been a learning experience for us as much as it has been hopefully for you. So we're really interested in hearing how the session went, what you thought of it. Please be honest so we can adjust and tweak. And then also let us know if you do want future sessions, if this was useful for you, and then we can try and sort of adjust and plan for future sessions based on your feedback going forward. Additionally, there will also be a short quiz to complete. So remember, if you've stayed for the full session and complete the quiz and get at least 2 questions right, you will receive a certificate. Gina has now posted the link for session 3, the feedback form for session 3 in the chat. Please remember that the earlier link is for session 1. So when you open this link, it should say session 3 feedback. Great. And so with that, I think I will end the session and give you 3 minutes back into your day. Once again, from the EDAM team, we're really, really happy that you joined. Thank you so much for the attendance over the past few days, and we hope to see you for the next session, or hopefully to see you for another sort of seminar series, not the next session. This was the last. Thanks, everyone.